Hey everyone, welcome back to discussion 29. We're going to start working on problem D01 and D02. So we're given a setup with two radio transmitters that are each, they're both a kilometer apart total, right? So then they're a half kilometer from this center line here. Okay, we're told they're coherent sources which are out of phase by 1/4 of a cycle, which is pi over 2 radians. Each signal emits intensity I naught. So each one emits I naught. And we are one of them is out of phase by pi over 2 radians. Okay, then we're told I have this airplane here. This airplane is flying along this direction. And then we're asked to find what is the intensity that the airplane receives at point O, which is right here. This is point O here. Well, it would be useful to just kind of stop and sort of look at the physics of the system that we have. So here we have two, these are radio waves, so this is light, right? These are being emitted from these two sources, and then they're spreading out and meeting and interfering here, right? This is very similar to a setup that we have with the double slit experiment, right? So we have some emitted light source here, and then once they hit these little holes, they come out. It becomes something similar to two sources, right, where they cross. And then, so you have this interference pattern here. And then you're going to have, well, the interference pattern is going to be here on the wall, where you have maxima and then you have minima here, right? So hopefully you've seen this at least a little bit. If not, that's okay. But we're going to use some similar concepts from here. Also, note that we have since these are just constantly emitting this light, right? And it's like a constant source of radiation, right? And so now we have a standing wave. And so essentially what I'm saying is, since these are both emitting and they're constant, there's going to be a standing wave interference pattern right along this line, like this. So there's going to be some interference pattern here. Okay? And now on our worksheet, there's also in the book, there's a relationship where we have a basic superposition principle, where we essentially just add up the waves that we're given, and then there's a derivation that you can go through. Essentially, what you end up with is something like this: 2 times the amplitude, we'll call this A naught, times cosine of delta over 2, where delta is our phase shift, sine kx minus omega t plus delta over 2. Again, where delta is the phase shift. Okay, and if we look at this, we can actually we can see a pattern here from something that we had before, right? This looks very similar to the wave equation, the functions for wave that we had earlier in some of our other lectures, right? Where we had an amplitude, which we called y max, times sine kx minus omega t, right? And now this, we still have this here, but now we just have a phase shift, which I'm not super concerned about. But also, within y max, this is our amplitude here. So this is our overall amplitude, which means that this can be considered our overall amplitude. Right? This was our general form from before. Now this is what we have. So if we're calling this the amplitude, we're after intensity, right? And we have a relationship with intensity that we can use. We have, okay, there's a whole bunch of stuff, and then there's like, you have your amplitude squared. This would be like your basic proportional relationship, and then we can call I naught anyway. The point that I'm trying to make is that you can take something that you're looking for here, a squared over a naught squared, right? This is your basic proportional relationship, which means that your intensity is going to be a squared over a naught squared times I naught. Right, well, let's, if this is a, and we take a squared over a naught squared, we end up with, so now I is equal to, so if we take this over here and we square both sides, we end up with 4 times cosine squared delta over 2 times I naught, right? So this is what our intensity is going to end up being. Now using this, so let's plug in here. So cosine squared delta over 2. Well, what's delta? Delta was from before we had, it was pi over 2. That's what we were given, right? So now if delta is pi over 2, so we put pi over 2 times 1/2 gives us pi over 4, which means that we're going to have 4 times I naught times, excuse me, times square root of 2 over 2 squared. This leaves us with 4 I naught, and then we end up with 2 over 4, so that's going to be, now our final intensity is 2 times I naught. Okay, next problem. D02. As the aircraft flies along AOB, where are we? As it flies along this line here, the time interval between reception of maxima, so from here to here, is observed to be 20 seconds. Which is kind of a long time if you think about it. If the aircraft is flying at 200 meters per second, what is the separation between adjacent maxima? So if the time observed between this point and this point is 20 seconds, it wants to know what is this distance. Okay, we're given a rate and we're given a time. We can find distance just using our basic d equals rt equation, because this is a standing wave. Remember, these are not, this wave is not oscillating, traveling in this direction or this direction. It's simply standing there as an interference pattern. Okay, so what that means is that we can take the distance between them is equal to our rate, which is 200 meters per second, times 20 seconds, and that gives us 4,000 meters. That's the distance between them. Okay, so that's the answer for that part, and then we're asked to find the frequency of the transmitters. Okay, so we can use a relationship that we have between frequency and wavelength, where in general we have frequency is equal to the velocity of the wave over the wavelength. And this makes sense because if we look at the units, we have meters per second over meters, and that leaves us with a unit of 1 over seconds, right? And that's frequency. So, well, we're told that these are radio transmitters, and that is light. And so now we know that the speed of light isn't really going to change. I mean, it's traveling through air, and it's pretty standard. It's going to still be 3e to the 8 meters per second. Okay, one thing is though, we don't know what lambda is. We don't know what the wavelength is. But looking at this double slit experiment, as I was talking about before, we actually have a derived relationship from here. N lambda is equal to d sine theta. And now where d is this d is the distance here. I'll draw a more clear diagram here. Let's just make it more clear. Okay, so here we have this basic setup, right, from before where we had we're emitting a source of light at this wall, and this wall has 2 holes in it. Now, as the light enters each of these holes, we have essentially what is 2 sources of light, and they combine and they interfere, and then we create a pattern over here, right? And so then we end up with some geometric relationships that we can sort of exploit. And so here's without the pattern. Right, so this y would actually be, if I can get this to work, here I'll do it. So y would actually be the distance between the 2 maxima. Okay, we have this big D, which is the distance from the sources to the pattern, right? To the wall. Okay, so what was it again? It was n lambda is equal to d sine theta. Okay, again, where d here is the distance between the sources here, right? Lambda is your wavelength. N refers to the order number of the pattern. So like if this is your first order maxima, this is in the center, right? From here to here would be order 1. Okay, sine theta. Now we have this triangle that we can sort of exploit here. That's what I was mentioning earlier, where we have y is the distance between them, the distance between the maxima, and then, okay, just going back just a little bit here. Okay, so now we want to figure out, really the distance is going to be this r here, right? We want to know what that is. But if we look, this distance between, where was it? Between the emitted sources, or here. So this distance here to here is 200 kilometers. And this distance between these maxima was 4,000 meters, right? So let's write these down. So this y is equal to 4e to the 3 meters. This distance is equal to 200 kilometers, which is equal to 2e to the 5 meters, right? Which means that r, when we plug this in to the square root of d squared plus y squared, this comes out to be, this comes out to be pretty much the same as d. 2e to the 5 meters. It's slightly larger by like 40 meters or something, but we're going to approximate it to be on the same order. Okay, it's just that this distance is so great that there's not really much of a difference between these two. Okay, so now using that, we can say, okay, well, we know d, we know that sine theta is going to be y over r, or in this case it's y over d, because these are essentially the same length, right? So we know what those are. So now we know this distance between the 2 sources is 1 kilometer, which ends up being 1e to the 3 meters. Y is 4e to the 3 meters. Sorry, I'm writing this in calculator notation. I hope that's not confusing for anybody. And this is going to be 2e to the 5 meters here, and this gives you a value if we take the first order, n, if we take n to be 1, This gives you a value of 4e to the 6 over 2e to the 5 is equal to 2 times 10 is 20 meters. That's how long your wavelength is. Just one wavelength. Okay, and then so we had this relationship here between v over lambda, where we can find the frequency. And remember, this is a radio wave, so we're talking about the speed of light. So this ends up being 3e to the 8 meters per second over, what was it? It was 20 meters, right? So this gives you a value of 1.5 e to the 7 hertz, which is actually reasonable, and it's in the range for a radio signal. We could also say that this is what was it, 1.5 megahertz. So we are told, well, let's just draw this picture. We're given a situation where we have two signals being emitted again, and this time we're up here where there's some observer. Okay, so this is A, this is B, this is C, right? And so the distance here is, this is AC and this is BC, right? Because these are transmitting and this person is receiving. Let's, you know, if we were to draw an ear or something. Okay. Anyway, the frequency of the sound waves is 2200 hertz. So 2200 hertz. So the frequency is 2200 hertz from both sources. They have the same amplitude, right? The speed of sound in air has changed. It's 330 meters per second. Receiver is at point C, like I said. Which value is given below for the difference in the distances is the signal at C a maximum. Okay. Pretty much we are given a relationship in the book, I'll say, but it's really a standard thing with these kind of problems. So n lambda, of course, is the n, where n is any integer value, and then we have lambda, which we have to figure out. We're given a frequency f, right? And remember from the last time that we have the speed of sound, or the speed over the wavelength is your frequency. So this is 2200 hertz. So now we can solve for the speed of sound is 330 meters per second. We know that. We're told that in the problem, even though that's not explicitly what we've been told every time. That's what we're using in this situation. So then we take that over 2200 hertz, which is 1 over seconds, right? So 1 over seconds actually cancels, and then that leaves us with wavelength is equal to 0.15 meters. Okay, so that's a good start. So now we're going to take n to be 1 because we just want to consider the first order, because that's right. We want to know where we are at a maximum. Actually, that's not true yet. Let's not jump to conclusions. So we're going to take n times 0.15 meters. That's your wavelength, and then we have the difference in distances, right? So this is just the absolute difference. So we'll say between AC minus BC, because we want the distances from the sources to the receiver, right? So these distances here, we want the difference between these distances. That's what we're after. Okay. We want the difference in the distances. So what we are looking for is delta D is equal to n lambda. So we'll just leave this here like this. We don't have to do any more solving. So this is all unnecessary, this part. This is unnecessary. For this problem, it's unnecessary. Okay, so pretty much all we got to do is we plug in values, we plug in integer values for n, right? Which could be 1, 2, 3, 4, 5, and so on, and then we try to see what we get. So let's do that. So the difference in distance for n equals 1 is 0.15 meters. Is that an option? No, it's not. So let's try again. We'll call that D1. D2 is 2 times 0.15 meters. That gives us also not an option. So we have 3.3. So if n is 3 times 0.15, that gives you 0.450 meters, which is an option. That is option B. So that's the one we're going to go with. So now at 0.45 meters, the signal is at a maximum for this setup. Okay, and just to recap, I used this relationship, and it asked us for the difference in D. Okay, next problem. What number are we on? D4. So we have similar setup, 2 loudspeakers, right? 2 loudspeakers making some noise. They are blasting, and someone walks here. This is 4 meters. Someone stands 4 meters away and says it's at a minimum. Okay, so we have these signals, right, going up this way. And then the person starts walking this way where 4 is going to be the radius, and she walks on the arc of a circle, right? So then we just go over here. We'll just say this is also 4 meters. I don't know if it's exact, but it doesn't really matter. And then, so this is on the arc of a circle. Something like that. Something like that. Here. I drew a better one. Okay, and what we're trying to find is this distance here. We are trying to find this distance, this new distance, where this person was able to walk along this arc and find where it becomes a maximum. Something like that. Something like that. Yeah, it looks the same. Okay, so this is what we're told. This is S1, this is S2. This is 4 meters. This is also 4 meters. This is 3 meters. So the initial distance then, if this is 4 and this is 3, this is a standard 3, 4, 5 triangle. This is going to give you 5 meters. That's going to be that distance. If you don't believe me, you can say, well, what's the square root of 16 plus 9? Well, that's square root of 25 is 5 meters. So, and one last piece of information, we are told, again, the speed of sound in air is 340 meters per second. It has changed again. That's fine. Let's just use what we're told. 340 meters per second. The speed of sound in air seems to change a lot around here. Okay. So, okay, well, let's look at this. We have the initial setup where we're not considering this. This one right here, right? This is what we're looking at. When this person is standing here, we can use that relationship. We're told that this is at a minimum. So let's find out what we have. We have n lambda over 2 is equal to the distance, the difference in the distances, right? So this is for when you're at a minimum. So we're told that we're at a minimum. So then, n lambda over 2 is equal to, what is the difference in the distances? Well, this distance from this source to here is 5 meters. From this source to here is 4 meters. So the difference is going to be 1 meter. Okay, and then we have lambda. This is going to be first order, because what we're told is that they were just kind of hanging out in front of the speaker and they found where the minimum was, which is over here. So this is first order minimum. So n is equal to 1. So then 2 times 1 meter is 2 meters. That's the wavelength. So lambda is equal to 2 meters. Okay, so now we can use that for when we go over here. So now we found lambda. We know what lambda is. So when this person walks over here and finds the maximum, we can use our other relationship that we know, which is n lambda, because we're not changing position. It's unlikely there's going to be a first order maximum between here and here. This is going to be first order maximum. Okay, so now this is the difference in the distances. Okay, and now we can work towards finding this distance, because that's what we want. So what we have originally, we had 4 meters here and we had 5 meters here, right? Let's put this back in black. Okay. So now we have 4 meters here and we have an unknown distance along the red line, right? So we have some source blasting, some source blasting. Okay, now 2 meters is equal to, what did I say? We're going to have the line S2 minus 4 meters. Well, that gives us S2 is equal to 6 meters. That's the distance. So hopefully that made sense. Just to recap, this is the distance that changes. So we go from 5 meters to an unknown number of meters, but S1 stays the same. Okay? Next problem. We're given a very similar scenario. So now we have S2 down here, emitting sound. We have S1 up here, emitting sound. We have this distance is 4 meters. Okay, this is the listener, so this is the receiver or observer. And now, again, we have another minimum in that spot. We want to know what is the lowest possible frequency of the emitted tone. The speed of sound in air has not changed since the last problem. It's 340 meters per second. Okay, well, we're asked for the frequency. And also remember that this is a minimum. So now we have to use this relationship again. Okay, if this is still 3 meters, then as from before, the same setup pretty much. This is 5 meters, right? So that means that delta D is equal to 1 meter again. So n lambda over 2 is equal to 5 meters minus, 5 meters minus 4 meters equals 1 meter. No problem. Well, that means that n lambda is equal to 2 meters. And then so what we have to do is we just have to plug in, here we go. What we have to do is we have to plug in for n, right? And then see what we get. So now if we take n to be 1, then lambda is still 2 meters. So let's try this now. Let's say, well, we know the relationship between the speed of sound and the wavelength, which is 2 meters. The speed of sound is 340 meters per second. The wavelength is 2 meters. This gives us a value, a frequency of 170 hertz, which is also 1 0.17 kilohertz. Now let's check and see if that's an option. It's option B. So I think that's your answer. So for the first order minimum, we get this frequency here of 0.17 kilohertz. And remember, I used this relationship to find all of that. Okay, that's it. Thanks.